I'm just coming from a tutorial. I'm just coming from an example class. I'm disappointed with the number of people turning up for example class and also for the lectures. Now I found out that some of you are still having difficulty. I know we started talking about power functions only last week, but still some of you are finding it difficult. So what I want to do today is to start with, guys, is to do more examples. On the power function. Okay. Now I started doing an example last Wednesday, I guess. Yeah, I started doing an example last Wednesday, which is this one. Which is exercise 75 in the list of examples. And I did the first two parts, I think, the first two bullet points. And I didn't have time to do the last one, right? So let me do that one now, okay? So this is... Oh, man. This is working. This is example 75, guys. Example 75, which I started doing last week, Wednesday. And, but I did not have time to complete it. Right, so you have... You have a random sample from a normal distribution, guys. Shh. Could you guys listen, please? We are testing this versus this. And I've done the first two, so I'm going to look at the last one. So all right, it says you choose a number between 0 and 99, and you reject the null hypothesis if that number is between 0 and 4. The question is to find alpha, beta, and the power function. So let's look at the power function first, which is the probability of rejecting Remember the definition of power function I gave you last week is the probability of rejecting the null hypothesis when given the parameter value mu. Mu here can take any value, doesn't need to be 0 or 1 or any specific number. It's an arbitrary number, right? So this is the probability that I is between 0 and 4 given mu. Now, what do you think this will be? What's the what do you think the probability that I is between 0 and 4 given mu? Remember, you're selecting a number between 0 and 99, and you're rejecting the null hypothesis if I is between 0 and 4. Now, tell me, how many numbers are there between 0 and 99? Huh? How many numbers are between 0 and 99? You have you have 100 numbers, right? And how many numbers are between 0 and 4? 5. So the probability that I is between 0 and 4, given this, is equal to 5 divided by 100, right? Which is 0.05. You guys with me? Yeah. And alpha alpha is the probability of type 1 error, which is the probability of rejecting the null hypothesis when in fact it is true, right? So this is probability that 0 is between and this is once again 5 divided by 100, which is 0.05. Are you guys okay? Yes? No? Yeah? Just shout at me. If you don't follow anything, just shout at me, guys. Beta is the probability of type 2 error. Yeah? Which is the probability of accepting the probability of accepting the null hypothesis given that H1 is true, right? And this can be written as 1 minus the probability of, by the negation rule, you can write this as 1 minus the probability of rejecting H0, right? Okay? And this is 1 minus the probability that I is between 0 and 4, given mu is greater than mu 0. So this is 1 minus 5 divided by 100, which is 0.95. All right, guys, is this clear or no? Or are you lost, guys? It seems some of you are lost. No. Because here, whether you accept or reject null hypothesis depends on only one thing. That is, whether the number that turns up is between 0 and 4. And there are 100 possible values you can have, 0 to 99. So the probability of rejecting is always, it doesn't matter what the value for mu is, the probability of rejecting is always 5 divided by 100. Yeah? And similarly, the probability of accepting is always 95 divided by 100, right? Does it make sense? Yeah? All right, guys. So that's the question. That's complete. So I'll put this here, guys. Maybe it's too large for you, some of you. Okay. Now let me do one more examples because I saw some of you guys struggling in the example class today. So let me do one more example from this list, right? This is this. Oh, can you say this, guys? Yeah, it's this one. Maybe I will. All right, it's this one, guys. Is number 50, is it 55? Yeah, example 55, guys. All right. So this is also a question on power function. So you have the rejection rule is that x bar is a sample mean is greater than k. So basically you have, you're testing for mu equal to mu 0 versus mu equal to mu 1, where mu 1 is greater than mu 0, right? And we are told that we reject the null hypothesis H0 if x bar is the sample mean is greater than a constant k. The first part is to find the value of k such that the rejection region with significance level alpha equal to 0.05, right? So we want to determine the value for k so that, remember, I think I told you this, guys, to last week. Do you guys know the name significance level? What is another name for it? The significance level is the same as the probability of type 1 error, remember? Didn't I tell you this last week, guys? The significance level is equal to alpha. Alpha is the probability of type 1 error. So, but we know alpha is we know that alpha is the probability of rejecting the null hypothesis when it is true. Okay? So that's the probability that x bar is greater than k given this. Now I did 2 or 3 examples in the example class, just from 3 to 4 today. Now can you tell me what's the next step I should do? Because I just finished doing 2 or 3 examples. What should be the next step, guys? Come on, guys, you know what I'm asking for. The next step should be to standardize this, right? To standardize this, you need to use the fact that x bar has a normal distribution with parameters. This is stuff we did in week 1 or 2. So please, if you could look back in your lecture notes, you will see this result, right? I think I even proved this result in week 1 or 2. Okay. So I'm going to use this result to standardize this, right? So I'm going to subtract mu 0 on both sides and divide by sigma squared by n. Sigma squared is 1 because you are told sigma squared is equal to 1. All right, so it's going to be 1 by root of n. 1 by root of n. Do you guys see what I've done? I have subtracted mu 0 both sides and divided by the square root of this, which is 1 divided by root of n. Now, this guy here must have the standard normal distribution, right, because of this, right? Okay. Now we don't need the conditioning anymore because I have made use of the conditioning to argue that this has the standard normal distribution, and therefore I have made the conditioning that mu is equal to mu0 is not needed anymore, right? So this becomes equal to this, right? And this is 1 minus the probability that and this is 1 minus phi okay. Right, now remember the question, you should look at the question over there, guys. The question is to find the value for k. We know the value for alpha. Alpha is 0.05. So basically you have this equal to 0.05, and we need to solve this equation for the value of k, right? So this implies that yes, and this further implies your answer. The 9.5, you get the 0.95 because of the one here. You get this, yeah, and then solving this equation, you get k to be equal to mu0 plus 1 over root of n So this is the answer to the first part of question. So this is the value for k. This is the value of k determined by the fact that the probability of type 1 error or the significance level is equal to 0.05. You guys with me or not? Okay. This is only the first part of the question. Now, if you look at the second part, also determine the sample size n needed for testing mu equal to 10 versus mu equal to 11 by this procedure so that beta is equal to 0.05. Yeah? Okay. So we are looking for guys, we are looking for testing mu equal to 10 versus mu equal to 11. And we are told that beta, remember beta denotes what? Beta is the probability of type 2 error, right? We are told that beta, which is the probability of type 2 error, is equal to 0.0. Oh, sorry guys. It's equal to 0.05. And the question is to determine the value for n. N is the sample size. All right. So let me show you how to. Let me take this away and put this here, guys. Sorry, I need to. Okay. All right. Now this implies, guys, the probability of type 2 error is the probability that we accept H0 when mu is equal to 11. Yeah. Now, if you look at the question here, guys, you will see that we reject the null hypothesis if x bar is greater than k. So we will accept the null hypothesis if x bar is less than or equal to k. Yeah? Now, once again, I'm going to use this standardization, right? Remember what I told you a minute ago, guys. X bar if you look at week 2 lecture notes, you will see this result, that x bar has a normal distribution with these parameters, right? Okay, now I'm going to use the standardization. So I'm going to subtract the mean. Now what's the mean, guys, here? It's equal to 11, right? I'm going to subtract mean on both sides, and I'm going to divide both sides by the square root of this. Sigma is 1, right? So it's 1 divided by root of n, 1 divided by root of n. Yeah? You guess with me? Yeah? I have subtracted the mean and divided by the square root, right? Now, we know that this guy is going to be standard normal, and this guy is root of n times k minus 11 is equal to 0.05. Once again, the conditioning disappears. The conditioning is no longer in this step because I have made use of the conditioning to argue that this has the standard normal distribution, right? So all right. Now, taking the inverse both sides, you get this. And so root of n now this is where I'm going to do the following. Remember, we have a formula for k, which is this one, right? This is the formula for k. So I'm gonna sub it in here because we know the value for k is equal to this one. And mu0 in this formula, mu0 is equal to 10. Because remember, this is the hypothesis we are testing. This is mu0, right? So your mu0 is 10 plus 1 over root of n Do you guys see what I'm doing, guys? Because we know the value for k must be this, yeah? I'm just subbing in place of this k, I'm subbing this formula, guys, with mu0 equal to 10, right? So this becomes 10 minus 11 is minus 1, so it's minus root of n plus phi inverse 0.95 equal to phi inverse at 0.05. Okay, and further simplifying this, you get root of n is equal to phi inverse and therefore the final step, n, is the square of this, in other words. Are you guys with me? It looks like a long process, but these are the kind of questions you may get in the exam, especially in the final exam. Does it make sense or not? Yes? No? Are you serious, guys? So you see, this is a two-part question, where the first part is asking you to find the value for k, right? K is the number in the rejection rule. The second part is asking you to find the sample size n, given the value for beta. Beta is the probability of type 2 error. Yes? Are you sure, guys? So I really want you to master this, because every year in the final exam you will get at least one question on the power function, and power function is a lot of people struggle with that. Now let me. Are you guys okay with this, or not okay? Anyway, just make sure you understand this kind of concept, guys. All right. Let me do one more question, then I'll move to something. I'm only doing questions from the examples booklet, which are not covered in the problem sheets. So I think I told you guys before that. I told you guys before, by the end of this course, you will have done most of the examples in the examples booklet, right? If not all. So I want to do is this one is question 84. Right? Right, so you're testing this versus this, where sigma squared is the variance, S squared is the sample variance, N is the sample size, and this is a percentile of the chi-square distribution. All right, now the question is to find an expression for the power. So we want to find phi at sigma squared. Remember, this is the notation. This is the notation for the power function, right? Which is the probability that we reject this is the probability that we reject the null hypothesis given sigma squared. Yeah? Yeah. So this is the probability that now, we are conditioning on the fact that the true population variance is sigma squared. Now, what you have here is sigma 0 squared. So the first thing you should do is to replace, the first thing you must do is to replace sigma 0 squared by sigma squared, right? And because of that, you need to multiply it by the same thing. All right, now I'm going to take this guy here to the right-hand side, right? And you will get now let me ask you guys, what do you know about this? You tell me what distribution will this have and why? Yeah? Come on, guys. You should know this, guys. We didn't do this long time ago. We only did this 2 weeks ago. Do you guys remember this? Do you guys remember this, guys? This one, equation 72. What you have here is the same as this. These two are precisely the same, right? Okay? And by this equation, this has a chi-square distribution with n minus 1 degree of freedom. Right? So by equation 72 in the lecture notes, now once again, when I moved from this step to this step, I have removed this conditioning, because this conditioning has been used to argue that this has a chi-square distribution, and therefore we don't need it anymore, right? So you no longer need the conditioning, right? Right. So this you can write as 1 minus the probability okay, and that's it. So this is the answer to the power. The question was to find the power function of sigma squared, and we have done just that. Okay. Are you all right, guys, or no? I mean, power function is really an important concept. You must do lots and lots of examples, guys, to familiarize with power functions. Okay. Right. Okay. Next, I can do more examples, but maybe later on, not today. Maybe tomorrow I will do more examples. But for the moment, let's move on. I want to move to the next page in the lecture notes, which is page, starting on page 20 and 21, right? So the first thing I want to talk about is oh, guys, sorry, guys. Right, the first thing I want to talk about is one sample inference. one sample inference for the population mean, right? So suppose you have a random sample from a normal distribution with these parameters, and assume that the value for sigma squared, is known, right? In this case, there are three possible tests. There are three possible tests for the population mean. The first is mu equal to mu 0 versus not equal to. The second okay, so there are three possible tests, and I'm going to put them I'm sorry about why this is blinking. This is a two-sided test. This is a one-sided test. This is also a one-sided test, right? And the corresponding rejection rules are as follows. For the first one, the rejection rule, we reject the null hypothesis if right. This is the rule for rejecting the null hypothesis. And for the second one, right, so these are the three rules, the three rejection rules corresponding to the three possible three possible hypotheses, right? All right, so this is in the case where the variance sigma squared is assumed to be known, but often in practice the variances are not known, right? So in those cases, you have to use some different tests, right? So here I'm going to consider the case where suppose, sorry guys, right? Suppose you have a random sample with the variance unknown, right? So once again, there are three sets of hypotheses you can have. You can have the hypothesis where mu is equal to mu0 versus mu is not equal to mu0. You can have the hypothesis where mu is equal to mu0 versus mu greater than mu0. And finally, you can have the hypothesis where mu is equal to mu0 versus less than mu0. Yeah. All right. So there are three sets of hypotheses. Yeah. And in this case, you will reject H0 if root of n times s. I will explain in a minute what these simples are. Yeah. And in this case, you will reject H0 if yeah. All right, so these are the three rules so these three rules correspond to the situation when the variance of the population is unknown, right? Now, you may ask me where these rules come from. I mean, how did I get these formulas? Or how do I get these rejection rules? Now, do you guys remember last week? You guys remember last week that I talked to you last week something about something known as the Neiman-Pearson test. Do you remember that? Or you already forgot, guys? Come on, guys. I thought you guys have better memory than I do. Yeah, you guys, I talked about the Neiman-Pearson test last week, yeah? You remember that or no? NP test or the Neiman-Pearson. I'll show you where it is. If you look back in the notes, you will see that. Do you guys remember this test? I talked about this last week. Yeah? Maybe you have too many midterm exams to take. Is that why or what? Yeah? Yeah. Come on, guys. You remember this, right? So this is known as the Neiman-Pearson test gives the most powerful test. So if you have a set of hypotheses, yeah, you can use the Neiman-Pearson test to give it will give you a test that is most powerful. In other words, you cannot find any other test that has a better power function than the Neiman-Pearson test, right? So it's the best power function that you can get is by using the NP test, right? Now, these tests, this one, this one, this one, this one, this one, and this one, all these 6 different tests I have given you are derived using the Neiman-Pearson test, right? Now, I don't have the time to go through all 6 of them, yeah? But maybe I will do one of them maybe later on, okay? But if you have time, I mean, I know, well, especially if you have finished all the midterms, you probably have a lot of time. Then you may want to apply the NP test, right, and see whether you can get these 6 different formulas, right, for the rule of rejecting the null hypothesis, right? All right, so that's what I wanted to say, guys. So these now, before I go to the next section is on inference for the population variance, right? I will go to that section maybe tomorrow, but before I do that, let me do just one thing. So I'll put this here, guys. Right, let me call this, let me give names, all right, so that I know. Let me call this 1, 2, 3, right? 4, 5, 6, right? Now, what I'm going to do now is I don't have the time I don't have the time to go through all 6 cases, but I will just derive the power function for number 4, right? All right, so it's pi of mu, which is the probability of rejecting H0 given mu, which is this, yeah? Now, to simplify this, guys, the first thing you must do is to get rid of the absolute sign. Right? This is what you get, right? You should remove the absolute sign. This is the same as this happening or this happening, right? Okay. Then the next step is to remember we are conditioning on the true population mean being equal to mu, so which is not the same as mu 0. So the next thing to do is to replace this guy here, these 2 guys, by mu, right? So I'm going to do that. I'm going to introduce a minus mu here. So I need to introduce a mu. Yeah. Right. The next thing is I'm going to group these 2 together. I'm going to group these 2 together, and I'm going to take them to the other side. Take them to this side. Right? So if you do that, guys, you will get right? Now, I'm going to ask you a question now, just to check your memory. I know you guys have. Can you tell me about this? What distribution these two guys have? It's in the lecture notes, guys. I can give you a spare copy if you want to have a look. Yeah? What distribution do these have? Come on, guys. It's not, we didn't do it, we did this only. You've seen this before, right? This one here. This is the same as this, isn't it? This is the same as, these two are the same, right? Now this has a t distribution with n minus 1 degree of freedom, right? So by equation 78, yeah, what you have is a t variable with n minus 1 degree of freedom greater than O right? Okay, guys? Yes? All right, the final step, because these two events are mutually exclusive, right? You can write this as a sum of probability. All right, by the way, we don't need this conditioning. I shouldn't have put this because I shouldn't have put this because I mean we have made use of the conditioning to argue using equation 78 that this and this have the t distribution. So this conditioning shouldn't appear anyway. So the final step, guys, is plus just give me a sec, guys. I know I'm running out of time. All right, so this is the power function. So this is the power function for test number 4. I know I've done 6 tests, so I hope you can work out the power functions for the other 5 tests by yourself, right? And this power function, if you plot it on a piece of paper, it will be the most powerful that you can get. Because the Neiman-Pearson lemma says that the test obtained using NP lemma is the most powerful. It's the most powerful one. Right? In other words, you cannot have another test that is better. Right? Okay? All right, guys, I'll see you in a few minutes' time. I'm really disappointed with the number of people turning up for the example classes. So if you belong to the class from 5 to 6, could you please come to the example class? You should belong to the class from 5 to 6.